As Olivier said, I'm a physicist. I'm in a lab where we have several different topics, and we are a team of about 10 permanent researchers. This optics and imaging group, so we are doing mainly optics. We are also doing some purely acoustics imaging. And today I'm going to talk about an optical imaging technique, which is called photoacoustic. So there's acoustic in the title. Just about terminology. You will see in the literatures, in abstracts, in conferences, several terms. There's a term which is acousto-optic. Okay? And acousto-optic, this has nothing to do with what I'm going to talk about. Now, you may also see photoacoustics, you may also see optoacoustic. Now, optoacoustic and photoacoustic, there's absolutely no difference, okay? So based on like where you come from, which group you belong to, people would say optoacoustic. Tomorrow we'll have a talk by André Stiel, and I think he used optoacoustic. It's just exactly the same thing of what I'm going to talk about, okay? So photoacoustics, you have acoustics in there, and I'll assume that most of you don't know much about acoustics, and so I'll take some time to give you some really basic numbers and principle about the basics of what's called photoacoustic imaging. And then in the second part of the talk, I'll go to some more recent developments in our group, okay, biased by what we do. This is not going to be exhaustive at all, of course. So first parts, basics, and then some more recent research-oriented developments. Okay, before that, and I actually have this point that I'm going to use. Yeah, right, okay. These are two movies. These are simulations, numerical simulations, okay? And there is a first medium here and a soft tissue here, okay? And we have this situation, and there is another situation, and I'd like to comment both situations. So we try to focus the waves in those two situations. It worked well in the first situation on the left. It doesn't work as well at all, actually, on the right. Okay. Now, this is essentially cartoons, but they are actually real physics-based simulations. Okay, these are technically based on finite difference time domain simulations. This is why you're seeing those, those waves oscillating in time, which you never see in optics because we time average all the time. The intensity measurements are time average by definition. Well, this is what it represents. The situation on the left is actually the situation in optics, the one that you know. You can actually focus inside a tissue, a biological tissue, provided you don't try to focus too deep, okay? So typically 100 micron, 200 microns, maybe if you do 3-photon or 2-photon microscopy, you may get twice as deep, but you can't get much deeper. If you try to go deeper, say if this is a few centimeters now, an optical attempt to focus optical waves will end up with this. So even if you try to do focused optical spots in optics, then at centimeters or even millimeters depth, you get a wide field illumination because of what's called multiple scattering, okay? So pretty much all we see in this conference is sort of superficial imaging on thin samples, and thickness of those samples, they're typically a few hundred microns, okay? Today I'm going to talk a lot about very different scales, several millimeters in depth and centimeters in depth, okay? Based on what? Based on the fact that acoustics now is back on the left. This is acoustic focusing, but this can happen over several centimeters, okay? This is how images of babies are done, okay? We image several, even tens of centimeters inside the body, because as opposed to optics, soft tissue, pretty much soft, every soft tissue, so take away bones and air, soft tissues, for ultrasound, they are very weakly scattering media. So there's a fundamental difference between optics and acoustics. We are transparent to sound, actually, and ultrasound, okay? So this is why optics can help, this is why acoustics can help optics, because it's not scattered, let's say, at all. It's weakly scattered enough so we can make images of baby when you get an ultrasound image, but it's very weakly scattering, okay? So keep those two things in mind. You can focus ultrasound waves down to several centimeters in depth, and you can't in optics, okay? But keep in mind that optical waves, they do get it deep inside tissue. It just, they do get there in a multiple scattered way where you lose the ability to get diffraction limited resolution, so you don't do microscopy down to a micron anymore, okay? For those who have no idea about orders of magnitude in acoustics, so first in acoustic, there's no reference medium like the vacuum, okay? For people doing ultrasound imaging in the biomedical field, the reference medium, the one we would set the index as 1, is water, okay? And the thing is that as human beings and small animals, except for bones, we are sort of bags of waters from the ultrasound point of view, with some slight index in terms of acoustic index contrast, enough so we can get echoes from when you do a standard ultrasound image. But more or less, from everything I'm going to say today, just consider that soft tissue is a purely homogeneous medium for acoustics. And of course, it's not for optics. Okay? Numbers, this is actually the right units for most ultrasound imaging systems, about a millimeter per microsecond. If you go to the micron scale, this is 1 micron every nanosecond. This is the speed of sound in soft tissue, okay? Now, if you put wavelength and frequencies, a megahertz is a millimeter, 10 megahertz is about 100 micron, and 100 megahertz, which is already for ultrasound very high frequency, you're only down to 10 microns. So these wavelengths, they're huge for you microscopist people, okay? They're really, and to give you the range of standard, if you go to a doctor, whether you're a boy or a girl, to go to some ultrasound exam, you are here in between those two frequency range, okay? So the resolution of a standard ultrasound image is in the range of, it's sub-millimetric, okay? But it's far from being micron, as in optics. Okay, let's go directly to what is a photoacoustic image. Okay, these are photoacoustic images. I took those images from a review which is now, 7 years old, but still, this is very representative of what's in the field now as terms of state-of-the-art images. Okay, and there are different things to comment on those images. First, the scale. Okay, you can see that a given technique, photoacoustic images, they can go from, let's say, very, very large field of view images, okay, with a resolution on this one typically about 100 micron, down to more conventional images and field of views in optical microscopy, where you have optical diffraction limit and field of views the size of few, say, 10 to hundreds of microns, okay? But this is the same technology. So this is something that makes it very specific, very, very, specific in terms of this scalability, which you don't find in many, many imaging techniques, okay? Whether X-ray or MRI or optical microscopy. So this is one of its main advantage. The second advantage is if you look at here, those 3 images, they are in a regime where you wouldn't get such a good resolution at that depth. Here, this is transverse scaling, but you can just imagine that these are actually 3D data sets, mean intensity projection over depth, which are on the order of the scale bar. So this is an image over several millimeters in depth in the Z direction. This is also a 2D rendering image of a 3D rendering data set, and this one, of course, also is, okay? So the resolution of those images, say about 100 micron here, about, between 20 and 50 microns here. They are low resolution images as compared to microscopic images, but they are obtained at several, at large depth, optically speaking, okay? This is more conventional. This is what's called photoacoustic microscopy. So this is the same sort of features as conventional, say, fluorescence microscopy, except for the contrast. I haven't said what you're looking at right now in terms of what is the parameter we're looking at. So we are actually looking, these are optical images. So we're looking at some optical parameter, and the optical parameter we're looking at, well, this is first, acoustic is the mean to detect things. We are detecting acoustic waves, but we're getting optical images in the end, okay? Which is why I'm at this meeting rather than some acoustic meetings. By the way, you can actually, photoacoustic imaging, you can find in acoustic meetings and optical meetings, okay? Because we're detecting acoustic waves, so there are a lot of acoustic detection or acoustic methodology, but this is done in the end to get an optical image, which is why, it was actually brought mostly first in the optical community as a tool, as a useful tool. Now, more specifically, and this is very, very particular to photoacoustic imaging, it is sensitive only to absorption, not to scattering at all. So if you have a sample which would be purely scattering but not absorbing, you would just have a dark image. Okay? So it shares this particular thing with fluorescence imaging, that if you don't have absorption, then you just have a dark background. Okay, so this is why those images, they might look like fluorescence images for some of you because they're on a dark background, but you're not looking at fluorescence emission, you're looking to non-radiative absorption. Okay, it's a key thing. So actually, a good contrast agent for photoacoustic is a bad contrast agent for fluorophores. You want that the photons that are absorbed, they actually go into internal energy to temperatures rather than re-emitting photons. Okay. Oops, what is that? Sorry, must have pressed something bad. Sorry about that. There's a button below it. Okay. Back here. So we're talking about absorbed light. Now, in absorbed light, there are two words, light and absorbed. So actually, more specifically, I'll show you some equation, not much, but one equation where you see that the origin of photoacoustic signals, you need light and you need absorption. You need both. And everything that I'm going to show you assumes that light is in a wide field configuration where it's pretty much constant. So in the end, if you image absorbed light, you image absorption. So all the images that I've shown to you, they are images of non-radiative, let's call it like that, optical absorption. Okay. It is actually not a new effect at all. Okay, photoacoustics has been discovered by Bell, the same Bell that invented the telephone, and actually he discovered that effect. And before he invented the wired telephone, he invented the wireless telephone with this photoacoustic effect. So I'm not going to get into this, but this guy was really an amazing person. Okay, so this is something very old, and the reason why it didn't find that many applications at that time is that the level of light intensities you need is rather high. Okay, and why now we don't have any problems? Because lasers came in the 60s, and now we can have fantastic sources of light that are tunable, that are pulse if need be. So the advent of photoacoustic spectroscopy about 50 or 70 years ago was the fact that it was used to detect small amount of absorption by this effect. So I won't get into this, but photoacoustics is old, and this is only in the 90s that the first ideas to apply this effect to biomedical imaging, and in particular optical imaging, came. So we're talking about a technique that has been developed a lot. I don't have those fancy curves in the literature, but they're really booming from the years 2000 until now, okay? With many groups in the world, just to give you a flavor of what we're talking about. So those images, they're actually made based on these photoacoustics effects, and I'll try to guide you through how do we make those images, okay, and what are the physical principles behind those. Forgot to turn my okay, so okay, it'll be a little 10 less. Good, thank you. Okay, so in the first part of the talk, I'll give you basics, and in particular, not much equation, but I'll try to make you understand how the signal is generated. Okay, this is going to be my own equation. On the left, this term here is actually the D'Alembert standard wave equation that's valid either for electromagnetic fields or acoustic fields. And the key thing here is that this is the constant, supposedly homogeneous constant speed of sound in the medium. Okay, so if this would be zero, equal to zero, it means that you're in free space, and then you have free space propagation that you all know about. This is how you go to one plane of a microscope to another plane of a microscope, assuming that apart from the lens, you're propagating in free space. Okay. Now the second term, what it tells you that there are source terms, things that creates acoustic waves, anytime this term is non-zero. In this term, you have two things. You have an absorption of light, so this is the optical absorption coefficient, and you need to have light intensity varying in time. Okay, and then there is some conversion factor, which involves this coefficient here is the heat capacity of the medium. This is the speed of sound, the same as here, and this is the fact that when you heat any medium, it wants to dilate. Okay, so the transformation of optical energy, light intensity into some pressure waves go through the fact that if light is absorbed, it's going to heat up the medium a little bit. This is going to create stress, and stress is what an acoustic wave is about. This is pressure is a form of stress in liquids. It's isotropic stress, and then it's going to propagate. Okay, so you need absorption. This is something that belongs to the medium. This is what you want to image. And you need light. This is your probe. This is what you're sending in the medium. And it needs to vary in time. This is not a detail. If you turn a CW laser on, you'll never get photoacoustic images. So it's just basic stuff, but it's good to have in mind. Also something, so this is what I've just said. And now keep in mind that pretty much 95% of the setups in the world, they use nanosecond pulses, okay? So in a photoacoustic lab, people, they have nanosecond pulse for reasons that are This is the optimal duration that allows you to put as many photons as you can by being in the safety norms and getting a good signal, okay? So the people that don't do femtoseconds because they are short and they are not useful because they don't carry enough photon to make detectable photoacoustic waves, okay? And nanosecond is short enough on the other side to be considered like close to infinitely short as compared to acoustic scales, okay? So in a simple picture, you can get this image that this is a very short pulse for ultrasound, even if for many of you, nanoseconds is like continuous. But for ultrasound, this is short pulses. Okay? Everything I'm going to give you, orders of magnitude, they are actually for light excitation with nanosecond pulses. So if you want to do photoacoustic imaging, you need something to detect sound, and you need a laser, which is a nanosecond laser. Okay? Nanosecond pulse laser. Okay, I'll give you what's happening if you take a point-like absorber. It can be a nanoparticle. It could be like a fluorophore, a bad fluorophore, except that in the case of fluorophore, the intensity, the pressure would be so weak that you would not detect a single fluorophore. But a single nanoparticle you can actually detect. What's happening, if you send a nanosecond pulse, so 0, positive, negative, a pulse of intensity, what you can demonstrate by working on this equation is that you get a signal which is the time derivative of the nanosecond pulse. So interestingly, you get from a positive monopolar pulse of intensity, and when you time derivative, then you get a, you get a bipolar wave. Okay, and I'll come back to this movie. White is positive, gray is 0, and black is negative. So, okay, you have black and white, means that's a bipolar wave. And actually, the integral of that pulse has to be 0, means that the medium, on average, is at rest. Okay? So if you have a point source, this is what you get. Now, if you think about frequencies now, okay, what is a sound as a frequency, right? What is the frequency of the sound? In this particular case, if you use a 5 nanosecond laser pulse, the frequency of the sound you get when you take the Fourier transform of that is something which is in the range of, say, 50 to 50 megahertz. Let's put it like this. Okay, so 50 megahertz, it's half what the radio you're listening at on the FM radio. It is a rather high frequency. I told you that biomedical ultrasound imaging is between, say, 1 and 10 megahertz. So it's a rather high frequency. But this is the frequency you would get if you were trying to listen to a point-like absorber with respect to illuminated by the nanosecond pulse. Okay. By point absorber, what does it mean, point absorber? It actually means, for some reasons that I don't have time to explain here, it means smaller than the size of this pulse, which is an ultrasound pulse. And the size of this pulse in space, if you go back to the speed that I gave to you, take 5 nanoseconds, you transform that into physical length, you get about something like 10 microns. So small means small as compared to 10 microns, which for most of you is actually huge, okay? So anything like a nanoparticle, a molecule itself is a point source for photoacoustics. Now there's a situation which is very different. Now you take a droplet, let's say a droplet, which is being tainted with a dye. But now you take it big. What big means, it's the opposite of small. So now you take a droplet with an absorbing solution. You can consider homogeneously absorbing. Size, let's much more than 10 micron. By the way, 10 micron is about the size of red blood cell, about a cell, right? So this is this cutoff size. And what you can show is that if you illuminate that droplet with a 5 nanosecond pulse, this pulse appears infinitely short, and in infinitely short time, it is going to put some initial pressure rise in the droplet. And this, because again, absorption converts to temperature, which converts to pressure rise, and this pressure rise is going to propagate as an ultrasound wave. Okay. So initially, you have an overpressure within the droplet, and you let this relax, let's say. What's interesting is that this is a positive pressure distribution over a 0 background, and when you let that propagate in 3D, this is a very specific aspect of the wave equation, you get this. In particular, you get black. So it means that you get negative at some point. Okay? So I'm not going to go into the details of why this goes to black, etc. If you plot the time traces, the waveform that is detected outside this droplet by a point ultrasound detector, you would get this. You would get this N-shaped wave. Okay? And this has two parameters. The height of the N is actually proportional to the absorption coefficient. So if you double the absorption coefficient, you double the concentration of dye in your droplet, it's going to double the signal. And the length of the n, with the length in time, the duration in time, is actually given directly by the time it takes for the ultrasound to go across the size of that droplet. Okay? And from a time, you can go to a spectrum if you want to think in frequency. And you get a spectrum which is a, whoa, 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 whoa. This is an escape button. It's a very bad button. Which is next to the next slide button. Okay. I'll try to get concentrated on that button. So if you convert that to frequency, then you get that if you take a droplet, which would be 100 micron, which is the size of like a not too small but not too big vessel, you get frequencies which are 10 megahertz now, on average. And this is very interesting because 10 megahertz is the frequencies that the technology of current ultrasound imaging system actually use to detect waves. So essentially what it means is that if you shoot a 5 nanosecond laser wave to your palm, for example, then the vessels in your palm, which is like close to 100 or 200 microns, they will emit sound at the frequencies that will be automatically detected by a standard ultrasound machine. So you replace a pulse echo ultrasound machine by a laser for excitation, an ultrasound for detection, and you have a photoacoustic imaging system, okay? Which is very good, very good. You just have to buy a laser. The just have is not a just, because it's like these nanosecond pulse laser, they're expensive. So we're talking about several tens of thousands euros, which is one of the main bottlenecks. But apart from that, if you just add a laser, nanosecond laser, onto a standard ultrasound machine, then you have a bimodal imaging system, which does standard pulse echo ultrasound, plus optical imaging ultrasound through this photoacoustic effect. Okay. Now, there's something very important now. Some people here, in particular Andre Steele, tomorrow is going to talk to you about using contrast agents, molecular imaging contrast agents, potentially. They are actually point-like sources. So how do you understand the photoacoustic generation from point absorbers when you have many of them? Okay, so I'll try to illustrate this by this simple droplet example. You take a droplet of homogeneously absorbing dyes. This is the left model. And now I'm going to make that droplet by adding dyes one by one molecule by one molecule. This is what you get. So this is the N that I talked to you about on the left, and this is this time derivative of the Gaussian pulse that you obtain when you have only one. What's interesting is that if you take 2 or 5, then you add up, and you added them coherently. Pressure waves, they added up coherently. So because you have plus and white, they add up coherently with strong interference effects. And if you do more and more, what do you get? You get this. Okay, so in the end, if you look into a droplet full of point-like absorbers, photoacoustically, you don't see any difference, okay? You see as if it was a continuous distribution of absorbers. As long as they're close enough, and they're close, again, this length scale, they're closer than 10 microns. If you target things in biology, of course, the packing is going to be that it's going to be much denser than 10 particles per micron, okay? So in the end, most of the time, contrast agents, molecular contrast agents for photoacoustics, you can consider this as a distribution of continuous absorbers on the tissue at that scale, okay? Now, how do you make an image out of this? There are actually two different regimes, very different. So the first one is called photoacoustic microscopy, and this is related to optical resolution, optical diffraction limited images. And the other one is when you want to go deeper than multiple scattering, and then you use the resolution that is offered by ultrasound. These are really two different regimes. You need to be aware when you see a photoacoustic paper that you're either in the first domain or the second domain, okay? How does photoacoustic imaging, the microscopic regime, works exactly as a very standard, let's say, raster scanning based focused microscopy setup. It's just that, so light is focused, okay? And then you have a bucket detector, single bucket detector of ultrasound that is going to pick up the sound for every position of that focus spot that you raster scan over the sample, okay? And you can only do this if you can focus light. So this is limited to the same regime as standard optical microscopy, superficial depth over a few hundreds of microns at max, okay? Now the second regime is when you shoot light, wide field illumination. Even if you were actually trying to focus, at several millimeter and centimeter depth, you got wide field illumination because of this multiple scattering aspect. And now the resolution will come from the fact that you are going to listen with some spatial resolution coming from the ultrasound, which is not as good for optics, but which remains of, say, about 100 microns at centimeter depth. Okay. A setup for, so these two images that I've shown, red blood cells, this is an organelle, they are photoacoustic images used in that regime. Very interestingly, one difference, you can say, okay, if it's the same as fluorescence, why don't I do just fluorescence rather than photoacoustic microscopy? Because the contrast mechanism is not the same. You might actually look to fluorescence, and you might want to look to non-radiative fluorescence. In particular, when you do this, this is non-labeled. This is just the endogenous absorption from red blood cells. Okay, this one is different, it's been tainted, but this one, it is the natural contrast, okay, that you get for imaging red blood cells just by the fact that it's strongly absorbed, in particular, green light. Okay. The basic setup, a few seconds on this, it's like an epifluorescence microscope with scanning capability on the emission, except that you replace the PMT by an ultrasound transducer. And instead of plotting the PMT signal as a function of raster scanning position, you plot the maximum pressure amplitude that you detect. Okay, and when you do this, you get this. Something that I'm not going to talk too much about, but which is actually fundamental, is that you can do that at several excitation wavelengths. You need to do 2 scans at 2 wavelengths, and from this, for blood in particular, as endogenous contrast, you can derive the oxygenation of blood, for instance, which is a biomarker very important. For example, tumors that are fed by blood, how blood is oxygenated around the tumor tells you much. So you can actually make functional imaging. So now this is not just bright or not bright. This is a parameter which is the percentage of oxygen in the hemoglobin, which is the absorber that you're looking at. Okay. So to do this, you need at least 2 wavelengths, and then you combine the two images obtained at different wavelengths. So this is the key advantage as compared to fluorescence or complementary assets of photoacoustic images. You don't need to label blood to image blood, and you can do blood spectroscopy. So this is a spectroscopic imaging that you can use to derive, again, saturation of oxygen. This is the name of that coefficient. Okay. Now, this is less familiar to you, probably. How do you get images like this? So I'll try to explain in not too long time. So suppose the green is a piece of tissue here. This is multiple scattering. If you shoot light, even if it was pulsed at the surface, it would be wide field illumination at depth, again, because of multiple scattering. I set a collection of point absorbers here, or let's say not point absorber, let's say droplets of blood that would absorb. What will happen is that all at the same time, because light goes very fast at the scale of ultrasound, they will emit an ultrasound wave. What is an ultrasound wave by a point absorber? It's like a dipole for electromagnetic waves, except they are monopole waves. So they really emit spheres, isotropic spheres. And in 2D, this is what you are seeing here, those circles. Okay? Now, if you detect signals, so how you detect signals? This is something important if you've never heard of that, but this is the kind of probe that those of you who have been to doctor to get some ultrasound on the knee or for a baby, they put you on the belly for a baby, they put you a probe, which is like a line of 256 or 128 detectors on a line, okay? And so it's a liner detector. They are distributed, those detectors, and this is the time dimension. So these sort of image here, the data sets you are seeing here, are signals along the vertical time, which is dimension, which is time, detected on all the 128 or 256 detectors. Why do they draw trajectories? Because the difference in the signal is just a difference in the time of arrival for those waves to the detector. Okay, so this is the data set, and if you do sort of delay and sum algorithm, so if you do in a computer exactly what a lens in optics does, which is rephasing wave, a lens transforms a circular wave into a plane wave, right? So you can do that in a computer, and you get this kind of images, okay? And you get points. While these are not perfectly points, this is actually, you're looking at PSF of photoacoustic imaging here, okay? I'll talk about that a little bit. You can actually, if they're one by one, you can localize them. And if they would be blinking, you could do super resolution imaging based on localization. I'll tell a few words about that. Let's look at the PSF a little closer. So that's a point source in space. This is what you get as the data. And when you do the image, when you do this lens computational transformation that gives you the PSF, this is what you get. This is something very different from optics. You get a PSF which has a sign. I mean, white is positive and black is negative. And when you're going to add up signals from different points, they will add up coherently in the pressure domain. So you're not adding up intensities, you're adding up pressure waves, which are sine waves. And there are going to be strong interference effects, which are going to lead to many aspects that I'm going to talk about to you. But so keep in mind that the PSF, if you take the envelope of it, if you demodulate, it's close to a PSF in optics, except that here we're in the XZ. Okay, so the natural section plane in ultrasound is the is the XZ. Whether the natural cross-sectional plane in ultrasound in optical microscopy, it's XY, and the Z you usually get by having a scan. Okay, this PSF is not only signed, so it's a coherent PSF, but it's also strongly anisotropic, right? Only when you sort of low-pass filter it looks like this. But all the physics happens on that scale. So this is these kind of images that you could do. And in the second part of the talk, I'll show you that even if they look great, but some actually look waiting for that. But yeah, okay, I'll step away. Thank you, Olivier. Thank you very much. Okay, so now I'm going towards more specific stuff, but I'll try to gap the bridge between optics and acoustics by trying to give you some analogies. So I'm going to talk about 3 different things. Those super resolution things, quickly, I'm going to talk about minimally invasive endoscopy. I have seen that actually endoscopy is not a topic that is addressed in this meeting, and I'll talk about that mostly actually, and I'll explain what I mean. This is a test experiment that we did about 10 years ago now. This is a leaf that has been dyed with black ink, so we can have a nice structure rather than beads. And this is the photoacoustic image of that leaf when you put an ultrasound array on the top, okay? And this is quite bad, okay? Well, you would agree with this. Essentially, what you see on that image, you only see the features that are horizontal. The reason for that is that the features that are horizontal, they emit waves upwards. The features that are, it's like an antenna effect, the features that are vertical, they are going to emit waves sidewards, and we're not going to pick them up because the transducer is on the top, okay? So even those great images from Paul Beard's group in UCL, if you look at the YZ or XZ, that would be the same, you have this feeling that there are only vessels that are horizontal, parallel to the surface, but this is an artifact actually. There are vessels that are vertical, you just don't see them because in this particular case, the probe is on the top and just, it does not pick up the signals that are sent sidewards, okay? So that's a problem. Okay, because you're missing some part. This is what we call visibility artifacts. Some features, depending on their orientation, some vessels, they emit sound towards direction, you're not detecting them. This is another example. If you take an ultrasound image of the top of the palm here, okay, this is not very interesting. That's getting more interesting. You might have the feeling that there are 4 vessels here, okay? And I'll explain to you that there are actually only 2 vessels, and you only see the interfaces of the vessels for reasons that I'm going to explain. So this is another case of a visibility artifact. The reason why, just to give you some more physics, is what I briefly mentioned, the fact that when you add up PSF, if you add them up vertically, they cancel each other from neighbor to neighbor, okay? If you add up horizontally, it's a convolution that you're doing, then they don't average out. So you only see, say, horizontal features. If you prefer to think in the Fourier space, you take the Fourier transform of that PSF, and it gives you something that only has values toward the vertical K direction. Vertical K direction corresponds to horizontal plane waves, okay? So you only see the features along the horizontal plane waves. So that's a highly anisotropic PSF as compared to optics, where you usually have this round-shaped PSF in the main imaging plane. Okay, one way to get around this is actually instead of having one direction, you just take your probe and you do tomography, you go all around, and then you can get 3D images with all the features present. This is something that we did with Jérôme Gatto 8 years ago now. This is, again, a small theory, but it just tells you that the image you get is actually the image of the pressure distribution when you shoot the laser, convolved with this PSF, and because this PSF has this shape, then you get something weird. This is something with visibility artifacts. Something very interesting now, if the source, then great. If the source of photoacoustic signal is fluctuating, then you have a pile of images over time, And this pile of images, you can average it, and then you get that standard image. For those who were at Anne Sontag's talk yesterday, when you have a pile of images that have been obtained with something fluctuation, in Anne's talk yesterday, she used speckle illumination to make the signal fluctuate in time. If you study the variance or the standard deviation, then you can show, I'll skip the details, that the image you get is related to the square of your object now, convolved with the square of the PSF. Now, if you take a PSF which is sine, you square it, then it's only positive. And then there is no way anymore that you have destructive interference. And this is something very interesting that we use, and I'll just show you results. This idea, even before we actually understood the theory, it came from an intuitive idea by Ori Katz, at that time a postdoc with us, at the time when Thomas was a young PhD student, young and bright PhD student, and we were doing this thing. There is an absorbing sample here, and we illuminated it with a laser, coherent laser, that has gone through a diffuser. This creates a speckle, and so the field seen by the absorbing distribution is this. If you do it for several speckles, I told you that the source of sound is absorption times light. So if light fluctuates from one pattern to the next, then the source of photoacoustic wave is fluctuating, and you can do that statistical analysis. You can analyze the image. I'll go quickly. These are the conventional images on 3 different types of vessel mimicking phantoms. These are conventional images, and this is the images that you get when you study the fluctuation now. Okay? So you have a PSF here, which leads to destructive interference pretty much everywhere. And the PSF from the fluctuation image, which is also the random illumination microscopy image, photoacoustic version, gives you this. It gives you this, and this bad image that were at the top gives you this. The reason why it's black at the bottom is because we have less light at the bottom, so there is less absorbed light. But if you can compensate for this, then you can get a homogeneous image. Okay? Actually, this idea was great, but doesn't work very well, because in tissue, inside tissue, the size of the speckle grain, the optical speckle grain, is about a micron size. It's diffraction limited. And this becomes actually too small to be seen as individual speckle grains, because it's like when I went to this collection of point absorbers, it's like a continuous distribution, and you don't see the fluctuation anymore. And then we had an idea, well, some years later, let's say 8 years later, that instead of having the illumination that fluctuates in time, if you are actually trying to image something that moves, so red blood cells flowing in a live animal, then that provides sources of fluctuation. So now we have always the same illumination pattern, but the sample is fluctuating by itself. Okay, and this idea was inspired by Sophie, actually, this imaging technique where you have the assumption that you have fluorophores that blinks, and if they blink independently, if they are sparsely distributed, you do localization, but if they're not, you can show that the images that you get when you study the variance image is something that is related to the square of the cross-section, and also that has a better resolution on the way. So this is the stack of normal images. They all look the same, and you see only the horizontal part. If you subtract the average image, you get this. This is not better, but then if you do the average of the square of this, which is the variance or the standard deviation, then you get this. So again, by exploiting fluctuations, you can get much better images. This is something we've been working a lot, both on theoretical and experimental perspective. Okay, same thing. This explains why we only saw on this kind of images obtained with a commercial system only the boundaries. If you use the fact that blood is flowing, you can get the fact that these are actually single vessels rather than doubled, apparently, vessels. Just to show you, we're not only doing things in tubes. These are the standard images that you can get in a chicken embryo, which is a nice model where you have flows, and this is live imaging without being too complex, both ethically and experimentally. And this is the kind of image that we get with our fluctuation-based imaging techniques. Okay. Quickly, I mean, if you don't try, I'm not a fan of deep learning, but you have to recognize that sometimes it just works. Okay, so just to tell you that this is what we give. I'll skip the detail, but this thing is what we give to the network, training the network that it should give us this. Okay, this is this kind of images that you've seen. I won't go into the detail. This is the ground truth. This is what standard photoacoustic imaging gives, and this is what a well-trained network gives. Okay, just to tell you that even if you prefer physics, sometimes, I mean, these damn things, I mean, they work pretty well, I mean, even as a black boxes. Okay, super resolution. I'm not going to go into detail. One slide just to show you that we copy-pasted pretty much everything that was done in optics. Super localization-based super resolution imaging, fluctuation-based super resolution imaging, sparsity-based fluctuation imaging. With a standard setup, it was a proof of concept experiment. We have 5 channels crossing the imaging plane, and they're moving in time. And we could control the concentration of absorbers. If the concentration of absorbers is very low, then there could be one absorber at a time, and we could localize them and then average over time to get this localization standard images. If they are too concentrated, so you cannot localize individual particles, then we can do other tricks. But just to show you, this is a localization-based image, diffraction limited, acoustically diffraction limited, and we break the resolution limit. Same kind of setup, but dense suspension of absorbers. If you actually study the fluctuations, they say in this case that were the 6-order fluctuations rather than the variance, which is a second-order fluctuation, then you can get this kind of image. And this is more computational imaging, where you know that you expect to have a sparse sample. If you put that as prior information in the reconstruction algorithm, you can get this. So the message of this is that you can copy-paste pretty much everything that has been done in optics to bring it to photoacoustics. This was done in acoustic, in pure acoustics, by Michael Tanter, who actually came back from an optic conference about localization. I think that was given by Eric Betsick in 2000, just after he came to this Mifobio. And Michael said, okay, we need to do the same in ultrasound. In ultrasound, there are contrast agents that they localize our acoustic bubbles. We can discuss this more if you want. But this provided those fantastic images. This is depth, right? And this is several millimeters. This is something you wouldn't do in optics. In photoacoustics, this is one of the leading group in the world, in the US, just to show you that they actually used localization of single dyed droplets that they would inject in the brain of a mouse with a low enough concentration, so you could have a diluted suspension that you could localize one by one, and then by accumulating over time, because there is flow, there is no activation like in fluorescence, but there is flow in blood, so we can re-randomize the distribution of absorbers, then you can do localization, and they went from this diffraction limited image to this. Okay? I'm gonna finish in a minute, because I'm gonna sort of skip this one, because just to give you the context, this is 2001. For more than 20 years, people have tried to do live microscopy of the brain while a small animal is living, like moving freely. So to do this, they built, this is even a 2-photon microscope, they built miniscope, they put on the head of a mouse, trying to minimize the presence of the setup on the head of the, and to do this, they used fibers, let's say. And now the trend is people are trying to minimize the weight of those systems. So 2001, 2021, so same sort of images, same sort of technology, but better optics, better engineered stuff, but you still have this on the head of the mouse. One approach is actually to put everything on the other side of the fiber and try to have a bare fiber in the head of the mouse. The last remaining stuff is that you want to minimize the invasiveness of the procedure. This is a bundle of multi-mode single core monomode fibers. And for a given number of pixels in the image, the diameter can be big enough. One trend since about 10 years is to try to develop endoscopy based on multimode fibers. For the same number of pixels, multimode fibers, they are typically 5 to 6 times less in diameter. Converted to area, this is about 30 to 50 times less in area. So they can get much less invasive. So this is a schematic where this is using a multimode fiber. This would be using a rod lens, a green lens, or another multi-core of single mode fibers. And of course, this is if we try to insert an objective into the head of the mouse. I'm not going to tell you much more information, except that the difficulty, if you want to image through a multimode fiber, is that it's a complex system from the point of view that if you insert a point source in a multimode fiber, at the other side, you get a speckle. Okay? You can actually unscramble that propagation. If you shape at the entrance, then you can focus at the output. And this is a workshop that we brought here, Irene and Leo. They work a setup where they have wavefront shaping capability. This is actually an old setup with an SLM, and the setup we brought here is a setup with a DMD that goes much faster. And the idea is that you shape the optical field so that at the output in the sample plane, you have a focal spot. And you do this by shaping the focal spot, by scanning the focal spot. And then you can do a microscopic image, scanning based. And the one originality of the things we're doing is that we are using another fiber to detect sound. So the system that I invite you to check on Wednesday and Thursday with Irene and Leo is a system where we can detect fluorescence, if there are fluorophores in the sample, but we can also detect the sound that is emitted by non-fluorescent absorbers. So we can have a bimodality proof of principle endoscope that we'll be happy to show to you for real. So I'm not going to go to the details. You'll have time if you're interested to go see again Leo and Irene, and then this is this workshop, okay? And feel free to discuss with your photo has been transformed to a very bad resolution image. I don't know why. This is what they can do at the end of the multimode fiber, okay? They can scan a spot and then make like an epifluorescence image based on raster scanning, okay? But again, go see them and they'll be happy to show you better results than those preliminary results we had at that time about 3 years ago. Now this is still Leo, better resolved. And with this, I'd like to thank all the persons that have been involved with the results that I've shown today, and more specifically you for intention, and I'll be happy to answer questions if there are some.
Thank you. Some sports at the same time. I was wondering, the fluctuation-based photoacoustic imaging, which increases the resolution, if I'm not mistaken, it goes at the expenses of temporal resolution, right? I mean, if you would like to image activity, you would have to sample for a certain time, which reduces your temporal resolution, right?
This is absolutely correct, and this is the exact compromise that you have when you do localization. All those super resolution localization-based imaging that we see in optics, they're great, but the price you pay is time, in addition to labeling and stability that you need. But yes, now the advantage of this is that you can actually tune the number of images that you get. So you can compromise, but you can tune the compromise. If you are patient, I mean, or if your sample is stable enough, you can, in theory, wait for as long as you want to get any sort of resolution. Then you have a noise that sort of breaks that limit, but you're right, absolutely. So there's a trade-off to choose in between going fast and getting better resolution or better contrast, and doing single shot, which is the faster. Now, so something we're trying, actually, so we are trying to build a deep learning architecture where we train the network with experimental data where we have time. Okay, so we train the network with going to a bad image to a good image, and the good image, the ground truth, comes from images that we've paid a long, long time. But once the network is trained on a given class of objects that look always the same, then you can go to single shot. So that's the strategy. It's in particular the strategy followed by Bastien Arnal, who's a young researcher, CNRS researcher in the lab. He's trying to use this fluctuation, actually, to train a network, so then the network can work with a single shot. So we do really sort of starting to like those networks, even if I don't like the black box aspect of them. But you're right, this is the key point of those fluctuations. So currently, the factor of 2 is the resolution you break by studying the second order statistics. Typically, we need about 100 image. We are limited by the pulse repetition frequency of the laser. 100 hertz for millijoules per pulse is the kind of PRF that you have. So 100 hertz, we're talking about a few seconds. So very low temporal resolution, I mean, depending on, yeah, but thank you, very important question.
Thanks a lot, very interesting. So I'm wondering if beyond the index that you can measure, I'm wondering if you can, from the data you collect, infer information about the viscoelastic properties of the material in which the
yes, you could, but then you would actually, people do, but then it's purely acoustics. It's a whole field, right? So here, sometimes actually you've seen Olivier Touvenin here, he uses optics to measure viscoelastic properties, but here we're using acoustics to derive optical properties. So if your goal is to go mechanic properties, then with our techniques we do pure ultrasound. Okay. And just we don't measuring index, we're measuring absorption. So we're measuring the imaginary part of the index, if you want.